I am happy to introduce Francis Brown from EHES. He will speak about quantum field theory and arithmetic.
Thank you very much for the invitation. I'm going to speak about a problem motivated by quantum field theory. Now, quantum field theory is a general framework for describing the fundamental forces of nature and the interactions between fundamental particles. So we can represent a quantum field theory by certain types of edges and vertices. So here I've given the example of quantum electrodynamics, in which there are two edges and one vertex. The first type of edge is a directed edge, which represents an electron going from A to B, or a positron going from B to A. The second squiggly line, it represents a photon, and the vertex here represents the interaction between the two. So what physicists do is they build graphs out of these graph elements, such as these two, and each one represents some kind of process. So in the first one, if we imagine time going from the bottom to the top of the diagram, we have two electrons traveling along which interchange a photon. In the second diagram, we have a photon going along minding its own business, which spontaneously decomposes into an electron-positron pair, which then recombine at a later point and produce a photon. So what physicists do is they write down all possible interactions which can happen in their theory, and to every such graph, which is called a Feynman graph, they want to associate a probability amplitude. So this probability amplitude will be denoted IG, and it's given by a certain integral called the Feynman integral, which I will explain in a minute. And in general, this quantity will depend on certain the momenta of the incoming and outgoing particles, and the masses of the particles in the interaction. Okay, so it's not an underestimate to say that an enormous effort goes into computing these probability amplitudes. It's an enormous industry, and it's been going on for many decades, involving many hundreds of people. And almost all the predictions for particle collider experiments are deduced from calculating these quantities. So in this talk, I want to make some simplifications, and what we'll do is set all the masses to 0, and all but one of the momenta to 0. And in this case, it happens that the amplitude will have some trivial dependence on some overall momentum, which we can forget about, and all the data is contained in this number here, the coefficient. And so what we get from this is a map from graphs to numbers, and the purpose of the talk is to try to understand what those numbers are. Okay, so now let's write down some Feynman integrals. So for this talk, I'm going to take none of these fancy squiggly lines. I'm just going to take an ordinary graph, which is undirected, so just any old connected graph with no self-edges. And there's a condition on the graphs to be physical, which is that all its vertices have degree at most 4. This is because in all the standard physical theories, except maybe for gravity, there are no theories in which more than 4 particles interact at one point. So graphs with 5 edges going into a vertex are unphysical and are not relevant. So this condition will be written G in phi to the 4. It's just a notation. It says that the vertices are of degree at most 4. Now, to any such graph, we can associate a polynomial as follows. So it's a polynomial in variables indexed by every edge of the graph. And it's defined by the sum over all spanning trees in the graph. And then for every spanning tree, you take the product of all the edge variables which are not in that spanning tree. So what is a spanning tree? A spanning tree is a subgraph, which is a tree, so it's connected and simply connected. And it spans if it meets every vertex of the ambient graph. Okay, so let's do an example. So this graph here has 4 edges, And I've listed its spanning trees here. It has 5 spanning trees. The first one, for example, is the subgraph with edges 1 and 2. It's clearly a tree, and it passes through all 3 vertices of the graph, so it spans. So in the same way, you see that there are 4 other spanning trees, and the graph polynomial is the sum of the complement. So for each spanning tree, we take the edges not in the spanning tree. So here, alpha 3, alpha 4, and we take the sum. So in general, the graph polynomial is obviously homogeneous, and its degree is equal to the first Betti number of the graph, the number of independent cycles in the graph. So physicists call this the loop number, and I will do the same. So that will be denoted hg. So we have that the degree of the polynomial is hg, and I will always denote by ng the number of edges in the graph. So here h is 2 and n is 4. Okay, now to write down some integrals, we need to make some conditions on the graph to ensure that we get actually convergent integrals. So the first condition comes from physics, and it says that G is what's called overall log divergent if the number of edges is equal to twice the number of loops. Then the second definition is that G is called primitive if for every strict subgraph the number of edges is strictly greater than twice the number of loops. So let me perhaps just draw a quick picture. In the example, we had this graph. It has n equals 4 and h is 2. So indeed, it is overall log divergent, but it contains this subgraph, which has n equals 2 and h equals 1, which therefore violates the second condition. So this is not an example of an overall log divergent primitive graph. But anyway, with these assumptions, we define the Feynman amplitude by the integral of omega g, where omega g is just the standard projectivized differential form on projective space. And in the denominator, we have the square of the graph polynomial. The domain of integration is given by sigma, where sigma is simply the set of real points in projective space with coordinates, with positive coordinates. Now, the first thing to observe is that this is indeed a projective integral because the degree of omega g is obviously n. And as I said before, the degree of psi is h, so the degree of psi squared is 2h. But by this assumption, n equals 2h, so the total degree of this form is 0, and we get a well-defined projective integral. Okay, so the upshot is that so I forgot to say, that of course, the theorem is that this integral converges in this case with these assumptions. So that's a theorem due to Weinberg. So the upshot is that we get a very concrete map from primitive log-divergent graphs in 5 to 4 theory to positive real numbers. And the whole game is to try to understand what these numbers are. So let's do a trivial example. So here is a graph which satisfies all the conditions with 2 edges and 1 loop. It has 2 spanning trees, the edge simply the edge 1 and the edge 2. So its graph polynomial is just alpha 1 plus alpha 2. And to compute the integral, we just restrict to an affine chart, for example, alpha 2 equals 1. And then the omega g becomes d alpha 1. The graph polynomial is alpha 1 plus 1 squared. And the integral from 0 to infinity is very easily checked to be equal to 1. But this is the only example that you can actually do in less than about 20 slides. So this is slightly misleading. So the next non-trivial example is at 3 loops. There is a unique primitive log-divergent graph at 3 loops, the wheel with 3 spokes here, and its integral gives 6 times Riemann zeta of 3. And I should say at this point, these integrals are very hard to compute. In the first example, the graph polynomial is of degree 3 in 6 variables, so it's a very high dimensional integral. The graph polynomial itself has 16 terms already in this case, and the integral is extremely singular. So it's very hard to get this even numerically without scratching one's head quite a lot. At 4 loops, there's a single example, this one giving 20 Zito of 5. At 5 loops, there are many more graphs, but I've chosen a non-planar one here that gives 36 times Zeta 3 squared. And at 6 loops, there are yet more. Of course, the number of graphs grows very, very fast as you go up. And this is, I've chosen the most non-planar and most symmetric graph, the most difficult. And its amplitude is given by this number, n35, which is 27 over 5, zeta 5, comma 3, plus 45 over 4, zeta 5 times zeta 3, minus 261 over 20, zeta of 8. So we get some very particular and very strange linear combinations of numbers coming out. And what are these numbers, in fact? Well, these are known as multiple zeta values. So now let me define multiple zeta values. So these go back to Euler in the 18th century. So for any set of r minus 1 integers greater than or equal to 1, and any integer nr greater than or equal to 2, we define the multiple zeta value, zeta n1 up to nr, to be the following nested sum: 1 less than or equal to k1, strictly less than k2, strictly less than kr, of 1 over k1 to the n1, kr to the nr. Now, precisely because of this assumption that nr is greater than or equal to 2, this nested sum converges, and it defines, again, a positive real number. So in the case when r equals 1, of course, there's no nesting, it's just the simple sum, and we get back precisely the values of the Riemann zeta function, which is a complete anachronism, of course, because it was known to Euler almost a century before. Now, an important quantity that we attach to multiple zeta values is the weight. So the weight is going to be the sum of all the indices in the argument. So n1 up to nr. So this is important to remember. Another fact that may or may not be well known is that multiple zeta values form an algebra. For example, if we multiply zeta n1 and zeta n2, it can be written as zeta n1 of n2 plus zeta n2 of n1 plus zeta n1 plus n2. Perhaps if I can sketch the proof very quickly. So it's a completely trivial calculation. So you just decompose the domain of summation into 3 pieces, and that precisely gives the 3 terms on the right-hand side. So in the same way, you can imagine, it's just slightly combinatorially more complicated, that if you take any product of such expressions, you can rearrange the indices of summation to rewrite it as a linear combination of multiple zeta values. And the point here is that these relations are homogeneous in the weight. So you never get any relations between multiple zeta values of different weight. So that's a deep and very difficult conjecture that, that the multiple zeta values for different weights are linearly independent. Okay, so let's look at the weights of the integrals in these examples. So we had these 4 examples here. The first one gave 6 times zeta of 3, which is of weight 3. Now one can show in general that the weight of the multiple zeta value occurring, if it occurs at all, will be bounded above by the quantity ng minus 3. So this is the number of edges of the graph minus 3. So this graph has precisely 6 edges. So 6 minus 3 is 3, and indeed we get a multiple zeta value of weight 3. Same in this example, the integral is 20 times zeta of 5. The weight, of course, is 5. And twice the number of edges is 8 minus 3 gives 5 again. So it's equal. But something strange happens over here for these two graphs. In this graph, the weight is 36 zeta 3 squared. So recall that the weight is multiplicative. Weight is additive with respect to multiplication. So the weight is 3 plus 3 equals 6. And the number of edges here is 10. It's 5. It's a 5 loop. Sorry, it has 10 edges, absolutely. So 10 minus 3 gives 7. And we find that in this case, the true weight of the amplitude exactly 1 less than the expected weight. And same in this example. So we call this phenomenon weight drop, when the amplitudes have weight less than the expected weight. So this, before even beginning to try to understand what these numbers are, illustrates that already the notion of weight shows us that something tricky is going on here. There's something subtle going on about why these graphs have a drop in weight and why these graphs don't. Okay, so in the 1990s, David Broadhurst and Dirk Keimer made some extremely extensive calculations of these Feynman amplitudes. And so these are numerical calculations. What they do is they don't calculate it in this form. They do some transformations on the integrals and use some very clever techniques coming from physics to get extremely good approximations to the integrals. Then they use methods of accelerated convergence and use a lattice reduction algorithm to fit the amplitude with some multiple zeta value ansatz. And that's what it means to calculate these integrals in their context. So they calculate them numerically, and they find that up to, say, 30 digits, they agree with a multiple zeta value. So they found that for all graphs up to and including 6 loops, and some sporadic examples at 7, 8, and even 9 loops, they always found numerically a multiple zeta value. So out of this very extensive numerical work, the following conjecture was born. I've called it a folklore conjecture because it's been reconjectured so many times over the history of this subject by so many different people that it doesn't really make sense to attribute it to anyone. And the conjecture, which is totally reasonable, given the evidence, is that these integrals are always Q-linear combinations of multiple zeta values. So another reason for coming up with this conjecture is because there are two-dimensional quantum field theories and conformal field theories in which it's actually known that the Feynman integrals always give multiple zeta values. An example of this is, for example, the deformation quantization. It's a little bit different, but it certainly gives multiple zeta values in its Feynman integrals. So there were good reasons for believing this to be the case, and as I'll perhaps explain at the very end, Pierre Cartier had a very grand philosophy that well, we have a motivic, as I explain at the end, there's a motivic Galois group that moves multiple zeta values around in some non-trivial way, and that in the same way, therefore, the same group should be moving all the constants of physics around. So he called this a cosmic Galois group, sort of Galois group of the fundamental constants of nature. So we'll come back to that at the very end. Okay, so what do we know about this conjecture? Well, I spent a couple of years trying to prove this conjecture. And in 2009, I managed to prove that the conjecture is true for some infinite families of graphs, which have what's called vertex width at most 3. I'm not going to explain what the vertex width is. Some combinatorial invariant actually that I invented actually for this problem. It's some ad hoc thing. It just the theorem just gives a concise way to describe an infinite class of examples for which it's true, and it essentially contains the examples that were known, but not quite all of them, but most of them. Okay, so still in the positive direction, let's focus in on a very specific family of zigzag graphs. So the zigzag graphs are graphs obtained by you glue a sequence of triangles together like this, and then you connect the outermost vertices with an extra edge. So the index n denotes the number of loops. So this graph has 1, 2, 3, 4, 5 loops. It's zigzag number 5. And actually calculating these graphs had a long history in physics, sort of people sort of breaking records every 3 to 5 years or so. But in 1995, Broadhurst and Kreimer made the following completely explicit conjecture for the amplitude of these graphs. So it's some Catalan type constant times some factor here which depends on the parity of n. That's reasonable because if you think about the topology, when n is odd or even, the topology of this graph is slightly different. And times a single Riemann zeta value. Okay, of course, this is only valid when n is greater than or equal to 3. So I proved this theorem last year with Oliver Schnetz by a very sort of oblique argument, a complicated argument. It actually goes through multiple zeta values. You'd think that you could just get it on the nose with single zetas. In fact, the true answer is that this amplitude is expressible in terms of this multiple zeta value, or things like it. And we use a recent theorem due to Don Zagier, published in the Annals of Maths, that evaluated this particular multiple zeta value, consisting of a series of 2's, a single 3, and a series of 2's, in terms of single zeta values and powers of pi. So this particular theorem was something I needed to prove what's called the Hoffman basis conjecture for multiple zeta values a couple of years ago. So we were lucky that this was available. Now the comment is that this is in fact the only infinite family of primitive graphs in phi to 4 theory, the theory we're looking at, or in fact in any quantum field theory, whose amplitude has been proved or has even been conjectured. So there is no other family of graphs for which it's even possible to guess what the amplitude should be. And these graphs play an important role, as I'll explain at the end, that it seems, experimentally at least, that these graphs are the only graphs in phi to 4 theory whose amplitudes can be expressed as a single zeta value. That means if you take any of these other graphs, you will always get multiple zeta values. That's a conjecture. We can't prove this, of course. Okay, so that's another positive, another family of graphs for which we know something. Now, to give an idea of what the structure is in this world of numbers coming from graphs, there are many identities. The first of which, so I've selected just 2 of them. The first of which is a partial multiplication law. So in the case, which is not always the case, but when we take 2 graphs, G1 and G2, which have 2 trivalent vertices connected by an edge. So let me perhaps draw a picture. So these white blobs are trivalent vertices. Then I take another graph, G2, with another pair of trivalent vertices connected by an edge. And the rule is then that you glue the trivalent vertices together. Of course, there are 2 different ways you could do this. And having glued them together, you then delete the connecting edges. So that gives you an operation to fuse graphs together. And you get, so here I've done the example on the most simple case, in the wheel with 3 spokes. You get this graph here. And then the theorem is that the amplitude of this graph is the product of the amplitudes of the two constituent pieces. So you can ask, what happens when you switch the way of gluing the chosen pair of vertices around? Actually, you get the same graph polynomial, which is a theorem due to Whitney. Okay, so then a second relation, which is much more sort of mysterious, is the following. And you can show that every non-trivial graph in our class has precisely 4 vertices of valency 3. So what we can do then is define its completion, G hat, which is the graph obtained by adding a new vertex and connecting it by a single edge to all the 4 valent vertices. So here in this picture, the white blobs represent the trivalent vertices. They're not necessarily connected by edges. That's just a completely schematic picture. So you can do this. This holds for every possible graph in our theory. We always get its completion. And then the theorem is that if 2 different graphs have the same completion, then their amplitudes are the same. So what this means concretely is you take a graph, you add a vertex at infinity, here, this vertex, and glue it in and connect it to your 4 trivalent vertices. This graph is now 4 regular. And now you have the freedom to choose any of its vertices and delete it. And you get a graph which looks completely different from your original graph. The graph polynomial is completely unrecognizable, but it still has the same amplitude. So with these 2 things, what you can do is you can see that from this argument, we knew this graph was 6 times Zito of 3, so this is 36 Zito of 3 squared. So if I complete it, that means I add a vertex here and connect it to the trivalent vertices. I get a mess. But going back to the examples, you can check that the completion of this graph is the same as the one I've drawn here. And so that proves for you by these 2 relations that the amplitude here is the square of the amplitude here. And indeed, it's 36 Zeta 3 squared. So there's a very intricate structure relating all these amplitudes. And it's safe to say that we simply don't know what they all are at this stage. For example, you can show because we know that lots of them give multiple zeta values, by counting arguments, we know that there must be many more identities than the ones we're currently aware of. Okay, so it's much too difficult to calculate integrals, so instead I'm going to count points over finite fields. So for this, we define the affine graph hypersurface to be the 0 locus of the graph polynomial in affine space. Okay? So in all our cases, this is an irreducible hypersurface, but it's extremely singular. And in general, we just do not really understand the singularities of this thing very well. But the key point is that the graph polynomial had integer coefficients. So what we can do is take p a prime number and q a prime power, and we can look at the point counting function, which to every prime power counts the number of points over finite fields of this hypersurface. So very concretely, you just count the number of solutions to the equation psi equals 0 over the finite field fq. And that gives you a number. So we get a function from prime powers q to integers. And in 1997, Kontsevich conjectured that the point counting function is always a polynomial in q. So let's look at some examples. So we had these 3 graphs, the wheel with 3 spokes, the wheel with 4 spokes, and a non-planar 5-loop graph. And here I've computed the point counting functions for their affine hypersurfaces. And so you get something, q to the 5 minus q cubed minus q squared. And we see that in all these 3 cases, they are indeed polynomials in Q, for all Q. Okay, but what is the motivation for such a conjecture other than the fact that it seems to be true? And this comes from the general philosophy of motives. So the idea is that the amplitude, in fact any period, any integral of an algebraic differential form over some algebraically defined domain of integration, should be an aspect of something called the motive, in this case the motive of the graph, and likewise the point counting function should be a different aspect of the same object. So what we get is the following heuristic picture. There should be something called the motive, which I'm going to describe in a minute, and by taking its Hodge realization, in other words, we're looking at Betti cohomology or de Rham cohomology, we can integrate forms against cycles and we get numbers. So out of the motive, the Hodge realization should give numbers, and in particular the Feynman amplitude IG. On the other hand, the motive has an L-adic realization, and then by the Grothendieck-Lefschetz trace formula, we should be able to express the point counting function as something which depends on the motive as well. Okay, so then what does it mean for an integral to be a multiple zeta value? Well, the philosophy is that a multiple zeta value should come from a mixed state motive. More precisely, a mixed state motive over the integers. I'm not going to define this category, it's very long to define, and it's not the point of the talk. But there is something called the category of mixed state motives over the integers, and it is now a theorem that its periods are multiple zeta values. So that's something I proved a few years ago as a consequence of the Dell'Igny-Hauer conjecture. And it's certainly the case that if you take a mixed state motive, it gives a polynomial in Q. So what we have then are our folklore conjecture that said that the amplitude should be a multiple zeta value, now has two different versions. It has Konsevich's version, the point counting function is a polynomial, and it has a sort of stronger version that the motive is mixed state over the integers. Okay, but we should be careful because this is kind of just a heuristic picture. There's something wrong with it, I'll explain in a minute. We can't necessarily go from the number to the point counting function and back. That doesn't make sense. It's really just an analogy. So what is the graph motive? So we want to express the Feynman integral, which if you recall was the integral over sigma of this differential form. We want to write it as something cohomological. So it's entirely determined by the data of the graph hypersurface. So what we can do is take its zero locus, the zero locus of the graph polynomial in projective space this time, and that defines some hypersurface that I've drawn here as a circle. Of course, in general, it's very singular. The picture is misleading in that respect. It looks smooth. It's not. It's very singular. Then the other bit of data we have, because remember the coordinates in projective space are indexed by the edges of our graph, so we have canonical coordinates. We can take the graph, the coordinate hypersurfaces where the coordinates vanish. So we get B1, B2, B3, which form a simple X. And the differential form that we're integrating is a differential form on the ambient projective space with singularities precisely along the graph hypersurface. And the domain of integration is precisely the set of real points contained in this triangle. Okay. So the simplex defines some kind of homology class whose boundary is contained in B. That means it's a relative homology cycle. So the thing to do, the naive guess then, you want to package this into something cohomological. The naive thing is to look at the complement of the projective space with respect to the graph hypersurface and take its cohomology relative to B, where B is the union of the coordinate hypersurfaces. But in reality, actually, the situation is a lot more subtle than that, because, as you can see from the picture, the domain of integration actually meets the graph hypersurface in the corners. So if you remove the graph hypersurface, x bar, you actually throw away you throw away a tiny corner of your domain of integration. And that's not a problem in terms of the convergence of the integral. It says the integral is singular somewhere at this point. It still converges, but it's a problem for algebraic geometry because it means that sigma is not in fact not a homology class of this. So to sort this out, you have to do a local resolution of singularities, do some explicit blow-ups, and after a long story, which was done by Bloch, Inno, and Kreimer in 2007, they defined the graph motive to be some explicit blow-up of the diagram I've drawn, P minus the strict transform of the graph hypersurface relative to the total transform of the coordinate hyperplanes. And their theorem is that the Feynman amplitude is indeed a period of this thing. Okay, so there are only two main observations I want to make about this. The first is that this is a relative cohomology group. It's not an absolute cohomology group. We're really taking relative, we're dividing by something. And the second point is that we're looking only at cohomology in middle degree. It's only that degree that we're interested in. That's the only part that the period, that the integral is looking at. On the other hand, the point counting function depends on the compactly supported cohomology, actually in our case, the affine graph hypersurface, but it involves all the cohomology in all different degrees. So, and the amplitude only sees this part of something that's quite different, in fact. So the point is that the point counting function and the amplitude are actually not depending on the same motive. And this is the source of all the subtlety. But anyway, after that digression, we can take it that the Konsevich's conjecture, which said that the point counting function is polynomial, is some kind of vague analog of the conjecture that the integral is a multiple zeta value. Okay, so here's the history of what happened next. In 1998, Stembridge proved that the conjecture was true for all graphs without any conditions on the graphs, so not necessarily primitive or log divergent or completely general graphs. So for any graphs with at most 12 edges, the conjecture is true. And then a completely amazing result in 2003 due to Belkali and Brosnan. I believe they were actually trying to prove the conjecture, and they ended up proving that the conjecture is generically false. In fact, they showed that the point counting function is of completely general type. So what that means is the following, is that you take any scheme of finite type of the integers, you can look at its point counting function, and then you can always find a finite set of graphs such that a certain linear combination of their point counting functions gives back the function you started with. So you can express the point counting function of anything with graphs. And in particular, since not all schemes have polynomial point counting functions, take your favorite elliptic curve, then it cannot be the case that all graphs have polynomial point counting functions. So the conjecture is completely false. But then you'd like to run this backwards and say, okay, take my elliptic curve and construct from it a graph that gives an explicit counterexample. And their method produces graphs with enormous numbers of edges, typically tens of thousands. And in fact, the way they do it is by, it basically gives graphs with vertices of enormous valency, which are therefore extremely unphysical. So this theorem of Belkali-Brosnan, for several reasons, does not in any way contradict the folklore conjecture that the amplitudes are multiple zeta values. It could be that this thing, the point counting function, fails to be polynomial for graphs which are very far from being the ones we're interested in. So again, in the positive direction, I proved that the conjecture is again true for all graphs in this nice family. Okay, so even counting points over finite fields gets extremely hard. So we want to make things even simpler now. And in truth, the point counting function actually contains a lot of junk. So what we do is we observe that for the graphs that we're looking at, the point counting function is always congruent to 0 mod q squared. That means for every prime power q, we can write the point counting function as q squared times something modulo q cubed. And that something is well-defined modulo q, of course. So what we get now is a function from q, not to numbers, but to numbers modulo q. And we call this the C2 invariant. So the C2 invariant of a graph is the product over all prime powers of some number in Z mod ZQ. And the reason it's called the C2 is that if it were the case that the point counting function were polynomial, it's not always the case, but if it were, then this thing would just be the coefficient of q squared in the point counting function. So since the point counting function is defined over the integers, it would mean that there is a constant m such that C2 of g is congruent to m mod q. In other words, we have this we have a map from integers to this sort of poor man's version of the Adels, and very poor man's versions of the Adels. And whenever, if the point counting function is a polynomial, then our C2 invariant will be in the image of Z in this thing. So let's look at some examples. Going back to the first three examples we had before, here the point counting function, you see that they're all divisible by q squared, as they should be. So to get the C2 invariant, I just take the coefficient of q squared here, which is -1, and the C2 in each component is just -1 taken mod q. And same for the next graph, it's we get -1 mod q, but for this non-planar graph, it's actually divisible by q to the 5, so the coefficient of q squared is 0, it vanishes, and the C2 invariant is 0 mod q. And we know we're onto a good thing because we had this question of the weight drop. These graphs had maximum full weight, and this had a drop in the transcendental weight. And this precisely corresponds to the fact that the C2 vanishes for this graph. It tells us that the weight's going to drop. And it turns out, in fact, that all these coefficients in the graph polynomial counting function are complete garbage. They tell us nothing about the integral. All the interesting information is contained in just this part. So we can throw away all the rest. So in fact, the philosophy is, so this is a conjecture, that if we have two graphs whose amplitudes are the same, then we expect the C2 invariants to be the same. So the C2 invariant should be enough to detect when two graphs have different amplitudes. And sort of irritatingly, since we know that the completions, two different completions of graphs have the same amplitude, this implies that their C2 invariants should be the same. But we can't prove this. So we have this very concrete conjecture. You take two different graphs with isomorphic completions. So you add a vertex at infinity and delete a different vertex. And then we conjecture that the point counting functions modulo q of the one is the same as the point counting function modulo q of the other. So this is a very nice problem, I think, to think about. The reason it's subtle is because in the proof that the integrals have the same number is some kind of integral transformation, and you can translate that up to point into algebraic geometry, but it gets kind of messy. But in fact, the C2 invariants are much nicer than the full point counting functions, because they have many combinatorial properties which makes them easy to compute. So as I mentioned earlier, it's sort of a conjecture, sort of a theorem, in fact, that the graph has weight drop if and only if the C2 invariant vanishes. So here's an example of an identity. Between C2 invariants. So this is taken from a paper with Karen Yates, and we call this double triangle reduction. So what we do is, suppose that we started off with a graph of this shape. So this means A, B, C, D means that this is just the rest of the graph. You can connect anything you like to these vertices. But in between, we ask that the graph contain two triangles back to back, double triangle. Then we can take this graph and keeping everything that's outside the same, we can replace this configuration with a smaller one. And then the theorem is that if two graphs are related by this operation, so we call this the double triangle equivalence relation, then the C2 invariant of this graph is equal to the C2 invariant of that graph. So this is completely false for point counting functions. But what's nice about this is that you see that we started off with a graph here, and then the new graph has 2 fewer edges and 1 fewer loops. So we're going down. So it enables you to start thinking about doing inductions. And in fact, so this is just a small part of a large family of identities which enable you to compute the C2 of the graph hypersurface in terms of hypersurfaces of smaller and smaller degrees. So it won't always be, these hypersurfaces won't always be graph hypersurfaces. There'll be some more exotic hypersurfaces defined in terms of the graph, which I defined a few years ago. And you can do sort of inductions relating the point counts of your original problem to smaller and smaller things. So behind this, what we're really doing is doing sort of fibering hypersurfaces over each other, and you get the point counts on the top is the point count on the bottom times the fibers, plus lots of correction terms, and the correction terms all go away because of the Chevalier-Warning theorem. So that's really what's going on. Okay, so there's a whole calculus to compute these C2s, which is very effective. So now let's apply this calculus. We can then start to look at graphs which are way beyond what anyone can compute, for which the amplitude can even be hoped to be computed. So this is way, way beyond what the physicists could compute. In fact, the best estimates for this integral would give it to 1 significant digit. And the size of the integral is several thousand. So the amplitude to this is known up to 1,000 approximately. So there's no hope of doing any numerical stuff for this. But the C2 invariant, because we have all these structures, we can reduce the graph hypersurface down and down and down and down. And at the end, via some changes of variables and some other tricks, we get to the equation of a singular K3 surface. And then using the classification of singular K3s and the modularity results known for these, we can prove that the C2 invariant of this graph, modulo P, so I'm only looking at the components mod P, are given by the Fourier coefficients of a completely explicit modular form, e to z to the 7, all cubed, which is of weight 3 and level 7. So here, of course, e to z is just the Dedekind eta function. And also this graph has, incidentally, vertex width 4, so it suggests that the previous results were in fact optimal. So this graph is modular. From that, we use the prime number theorem. So we know quite a lot about these coefficients. We use the prime number theorem to show that these, as p varies, these numbers vary a lot. So they cannot be constant. And therefore, this proves that the graph counting function cannot be a polynomial in Q. So this is slightly different from what's done normally. So if you think about each, so we have prime 2, 3, 5, 7, and then we have 2 squared, 3 squared, 5 squared. So it's normal to sort of look at the local zeta function and look at things vertically. So this traditional thing is to count points in families vertically and understand this function. We're doing the opposite. We're looking at in the transversal direction. And you see that the values oscillate in a terrible way in here, so there's no way that it could come from a constant. Okay, so even worse, if we go up to 9 loops, we find another graph here, which is now planar, and has exactly the same property as the previous example. So it's also modular. And in fact, it's very easy to see, because here we have a double triangle, by double triangle and completion, it almost immediately reduces down to this example. So this shows that Kontsevic's conjecture is false even for planar graphs. This is important because there's a long precedent in physics of taking planar limits of quantum field theories. So it's thought that, so there's a history of looking at restricting to planar graphs. Okay, so that conjecture is false for physical graphs, but that doesn't tell us anything about the amplitudes necessarily, because as I mentioned earlier, the point counting function and the amplitude come from different motives. So could it still be the case that the motive is mixed Tate? So it could be that these modular forms are coming from something in the wrong cohomological degree, and the integral just doesn't see that. So in a paper this year with Dimitri Dorin, we lifted all these point counting arguments to the level of cohomology. So that requires a fair amount of work, and in fact we were lucky that there's available a motivic version of the Chevalier warning theorem due to Bloch, Hénaud, and Marc Levine. So armed with this, we proved that in fact for this 8-loop example, that the integrand of the differential form defines a class in the de Rham cohomology of the open complement of the graph hypersurface, and its class in the graded weight 24th piece is of Hodge type 1311. And recall that the definition of being Tate in Hodge theory is that it should have Hodge numbers of type NN only. So that means that this is not a Tate class, therefore this cohomology cannot be mixed Tate. And the corollary is that the amplitude therefore cannot factor through a category of mixed Tate motives, any category of mixed Tate motives. So now that blows out the strongest version of the folklore conjecture as well. That's completely false. And from this, unfortunately, it's not possible to prove that a number is not a multiple zeta value. That's an extremely difficult transcendence problem. But if we assume Grothendieck's transcendence conjecture for periods, then the standard conjecture, because this is not mixed Tate, this means that this amplitude is not in the ring of multiple zeta values. In other words, every single version of this folklore conjecture is completely false, and false in a drastic way. Okay, so then we started with Oliver Schnetz. We thought we'd try and see what was out there. So we computed the point counts mod p, the C2 invariant mod p, for the first 13 primes. So the C2p is just, it's a number mod 2, a number mod 3, a number mod 5, and so on. If you count how many there are of such possible sequences, they're enormously large. And so the likelihood of accidentally finding something by chance is exceptionally small. So we did this for all 10,000 graphs up to 10 loops, and we found so far 16 modular forms. Here are their weights and their levels in this table, along with the subscripts indicate the first loop order at which they occur. So the example we looked at earlier is this one, weight 3, level 7. It's the only example that's been proved. So if you like, all these others are conjectures. So we conjecture that the corresponding hypersurfaces are modular. And in fact, it's worse than that because there are several graphs that give sometimes the same C2 invariant, and we don't know why. Another strange observation is that we find that there are no modular forms of weight 2 which occur. So that's kind of curious. Okay, so the conclusion is that all versions of the folklore conjecture, that is to say that the amplitude is a multiple zeta value, the underlying motive is mixed Tate, or that the point counting function is polynomial, all three aspects of this conjecture are completely true for small graphs, which is essentially the graphs that people were looking at, but completely false in general. But now physicists come back to you and say, I don't know, but you see, the integrals, the amplitude of a single graph makes no sense. That's not a physically meaningful quantity. In physics, we take the sum over all graphs, and that's the thing that we measure in experiments. So the thing to do then is to take the sum over all graphs, and it was hoped that somehow these bad examples would sort of cancel out with something. And you can show, in fact, that this doesn't happen. There's nothing for them to cancel with. So they remain at the bitter end, and sort of all bets are off. So what we found is that the numbers that come from physics certainly go beyond the realm of multiple zeta values, but we're not getting any old numbers. They're still highly constrained. For example, we found no modular forms of weight 2, and for example, there's no Zito of 2, for example. So the situation is much more complex and much more interesting than anybody imagined. And so now that the folklore conjecture is completely wrong, we're left with the question, what are the numbers and what is the class of motives that quantum field theory is picking out amongst the world of all possible numbers and motives? So this is joint work with Oliver Schnetz. What we did then is just try to look at what the structures are. So we computed, as I said, the C2s up to 10 loops, at least for the first few primes. And we found something that I think is completely amazing, and that there are basically 3 types of graphs. The first one is the graphs which have vanishing C2. So as I mentioned, these graphs have lower transcendental weight, and therefore, in physics, they will contribute in a very different way to the rest of the theory. Then we have sort of the nice class of graphs, which is the first few examples, where the C2 invariant is -1. And the absolute miracle here is that we found that all the graphs in this class are actually equivalent to one graph. And that's the wheel with 3 spokes. So certainly up to 10 loops, every graph that is not weight drop and satisfies Conservative conjecture is just in the equivalence class of a single graph with, if you apply double triangle and completion relations to the single graph. So that's, I find, incredibly surprising and completely unexpected. And then the third example is sort of the box in which we shove all the rest. These are the graphs for which the C2 invariant is non-constant. So the first example is at 7 loops, and they contain all these modular and wild examples, and many, many examples that we can't identify with modular forms. We have no idea what they are. All of these are counterexamples to the point counting conjecture. So essentially we're saying that either the graph is completely outside the scope, there's a counterexample to all the conjectures, or it's weight drop, or it's equivalent to a single example. And in this class, so this class is the one that people sort of were accidentally looking at, essentially. We find that the amplitudes for this graph aren't actually multiple zeta values. We expect them to be a very precise subspace of multiple zeta values, in which, for example, no even zetas and no double zetas should occur. So I can define this class very precisely. I won't do it here, but there is a very natural class that subspace of multiple zeta values, and it looks as if this is actually landing in this subspace. Okay, so I'll finish off with some very speculative considerations on the motivic versus the cosmic Galois group, as I promised. So what's the right way to think about multiple zeta values is as follows. So if Z denotes the ring spanned by the multiple zeta values over Q, then the way to think about it is as a kind of Galois extension over Q of transcendental numbers. Of course, we don't know that they're transcendental. They're extremely difficult conjectures in that direction. But that should be the case. And there should be a group which moves these transcendental numbers around in such a way that it preserves all the algebraic relations between them. So this is an analog of classical Galois theory where we have algebraic numbers, but instead of finite groups and pro-finite groups, we have matrix groups, or rather pro-algebraic groups. And in this case, the Galois group is something called the Galois group of the category of mixed-tape motifs over Z, which I didn't define. But this Galois group is something that structurally, at least, is very concrete. It's the graded Lie algebra of its unipotent radical is a free Lie algebra with one generator in every odd degree. And these generators correspond to the odd zeta values. So what this means, in fact, you can actually compute this Galois action. What it means is that sort of the infinitesimal version of this Galois action means that you can take a multiple zeta value and, conjecturally at least, you can differentiate it with respect to zeta 3, or differentiate it with respect to zeta 5. And this operation can be computed, and it preserves all these relations, all this very complicated structure of multiple zeta values. Now, so that's the picture for multiple zeta values. We know what the Galois group is. Now let's look at the ring spanned by Feynman amplitudes and try and do an analogy. So I take the set of all physical graphs, factor 4. Now what we know is, by these counterexamples, that we don't expect these numbers to be multiple zeta values at all. They go way beyond. But also, those which are multiple zeta values are actually very special linear combinations of multiple zeta values. We don't even get all multiple zeta values. But what we can do is play the following game. We can take the combinations which are multiple zeta values, and we can compute the action of the motivic Galois group of multiple zeta values. And so as we saw at the beginning, we had this N35, this very strange linear combinations with 261 and strange numbers in it. But what we find is that when we apply this Galois action, these numbers are preserved by the group. So this is absolutely incredible, because it means that all these funny coefficients, 261 and so forth, are sort of mirrored in all the higher amplitudes of higher graphs. They all fit together in such a way that all these numbers match up. And this, if it's the case that the group actually acts on these numbers, it has phenomenal predictive power for guessing the amplitudes. And so that the holy grail, therefore, would be a formula, much as we know formulas on multiple zeta values, a formula for the action of the motivic Galois group on graphs. And since we know that the zeta values correspond to zigzags, there should be a way to take a graph and somehow differentiate it with respect to a zigzag, sort of pull out zigzags, and give some combinatorial formula which would then tell you what the amplitude is without actually having to calculate anything. So the final question is then, this suggests that these numbers coming from physics, whilst they are not multiple zeta values, they're much more exotic, it looks like they might be closed under the action of some bigger, some different Galois group. And I suggest that this should be the cosmic Galois group that was alluded to at the beginning. I'll finish there.
So thank you very much for this interesting talk. Est-ce qu'il y a des questions? Is there any question?
It's a double question, in fact. What software do you use for your computation? And is it fully automatic, or do you have to hand help it?
What was the first question?
The question was about what kind of software you use for your computation.
What kind of software do you use for computations? Good question. So I use Maple. We used, so actually, yeah, we use mainly Maple. We do everything by hand. So I do everything from scratch. I don't, I'm slightly mistrustful of packages, so I like to do everything myself. For the graph generation, we use something called Naughty. So it's very hard to generate graphs up to isomorphism. We use something called Naughty, N-A-U-G-H-T-Y, which gives you the graphs up to isomorphism. Then to generate the modular forms, we used Sage. So to generate all these, we generated all these tables using Sage. Actually, at this point, I'd like to make a suggestion, because it's often the case that you have some scheme to find over the integers, and you want to know what it is. So you count points over small primes, and you get, if you can compute the first 10 primes, you get some sort of unique signature of your thing. And it would be enormously helpful to have a database where you could just type in this sequence, like the encyclopedia sequence, and it would just produce.
I think it does exist. I think there's a site where you can enter your.
Well, so we ended up having to. Well, I would love to know if you could suggest that to me afterwards.
I think such a site does exist.
It does exist. Very good. Okay. Okay, that would have saved us a lot of trouble at the time.
About the graph G8.
Yes.
How did you come to this graph? Does it come from the geometry, or is it in the other direction? You started with the graph and then.
Well, I knew that the theorems were too. Well, when I was trying to prove these conjectures, after a while, you start to realize you're going to fail, and in the proofs it becomes clear that what the obstructions are going to look like. So I knew that vertex width 4 was the place to look, and at 8 loops, there's a huge list. But so Oliver Schnetz went through all of them and produced. So in fact, there are 4 counterexamples at 8 loops, which are modular. So we have 1, 2, 3, 4, and so you reduce them down, but then 3 of them we can't actually prove that they're modular. It's just too difficult. So this one we were very lucky because we got down to a cubic in P3, and by some miracle, the Néron-Severi group is the Picard lattice is spanned by lines. So it was very, very quick to prove the modularity using what these guys have done. I was worried that you'd have to work very hard and use, do elliptic fibrations and really do a lot of work to prove the modularity. In this case, it's really the most simple and most beautiful example you can imagine. So we're very, very lucky in this case. But there are only four classes of graphs anyway. So that was the one that was the only one that we could do.
Other question?